What if there is a flame spread in a natural convection? Then the flow velocity instead of u infinity will be replaced by u b, which is the buoyancy induced velocity. U b is the buoyancy induced velocity, which is g nu g delta h c y infinity by cpg t infinity whole power 1 by 3. So, this is the expression which is available in literature. Okay. So, you can see that the g comes into play there, the buoyancy induced velocity. So, this is some expression which we can use for replacing u infinity by ub. So, here g is the acceleration due to gravity, nu g is the kinematic viscosity for the gas phase, delta S is the heat of combustion, oxygen mass fraction in the ambient, Cpg is the specific heat of the gas mixture, and T infinity is the ambient temperature. So, that means if you go back for this expression, thermally thin case, that is the expression which you have derived like this for this velocity. So, this is fine. But for the case of thermally thick case, u infinity is appearing in the expression. For natural convection, we can replace this by this ub. Okay. So, now both these thermally thin and thermally thick case, we have seen only the expressions for opposed flow, opposed flame spread, that is the flame is spreading in the opposite direction to the air flow. Okay, that may be in the forced convection, the flame propagates in this direction, u infinity will be in direction, or in the natural convection case, this is g, flame actually is ignited at the top, and the buoyancy induced flow will be in this direction, ub will be in this direction, and the flame spreads in the opposite direction to the buoyancy induced flow. So, these are the opposed flame spread aspects which you have seen. But concurrent flame spread, how to determine the velocity? But it is very difficult, because the concurrent flame spread is very complex. The heating length, pyrolysis length, etc. vary, and there are lot of non-linearities here. So, getting a expression for concurrent flame spread is not at all very easy, but some expressions are reported in Pellow 1995, which are very complex expressions. Basically, we can solve it by numerically and get the flame spread rate, or experimentally determine correlations we can do. But some expressions, like theoretical expressions, is not very easy to obtain. Okay, why? The concurrent flame spread, if you take, apart from conduction heat transfer, which was considered in the opposed flame spread, we say that the flame standoff is there, and heat and length also is very small. Since the flame standoff is also very small, only conduction heat transfer is predominant in the opposed. So, we can neglect the radiation. So, once radiation comes into play, it will be a very big problem. So, what happens here? Conduction heat transfer will be there, but radiation heat transfer, convective heat transfer will be large. Similarly, the re-radiation heat loss from the solid to the ambient also will occur, because the temperatures are very high here, because it is continuously being heated up by a flame due to radiation also. So, that is the reason. Then that is a significant value for xp, and the pyrolysis length also is much longer. Here the pyrolysis length and heated length are of same order. Here it is not so. Pyrolysis length also is very long. Apart from pyrolysis length, there will be a significant amount of heating length also. Okay. So, in this case, the Vf will be much larger than that we observe in the opposed flame spread. First point. Second one is this Vp, the Vf also will vary with time. It is not going to be steady flame spread rate. So, let us say if xp is the pyrolysis length, I can say Vf can be expressed as dxp by dt. Okay, so within the pyrolysis zone, this is the pyrolysis zone. Within the pyrolysis zone, the flame standoff can be small because the flame has to heat up the pyrolysis. You can see that the pyrolysis region goes like this. The depth increases, and towards the end, pyrolysis length, the depth at which the pyrolysis occurred has reduced. Okay, so by just assuming that within the pyrolysis length, the flame standoff should be small, and when the flame stands away from this, then the heating length will start eventually. Under that circumstances, we can say that the flame standoff is small, relatively small, and basically at the leading edge, and we can say that the flame standoff increases with x. From the leading edge, it is very small, but as we saw in the case of opposed. But as x increases, this is x direction, as x increases, this will increase, the flame standoff increases as x power 0.5 in the case of forced convection, or x power 0.25 in the case of natural convection. So that means as the location increases, we will non-uniform heating, non-uniform pyrolysis occurs. Okay, so that we have to understand. These are the complexities. So that means we can get some expression for a given configuration, but generalized configuration cannot be got. For the opposed flow, what will be the configuration? Basically, we can easily give the value because it is a steady state flame spread. So keeping that in mind, people have come up with some expressions. Okay, let us say in forced convection, here you can see that flame spread rate in centimeters per second for concurrent thin case and concurrent thick case is reported. Thin case is done by using the paper, thin paper, and thick case is PMA. Okay, so let us say concurrent thin case. First, you can see that the flame spread rate are much higher. So in this range, order of 1 to 10 centimeters, that range it appears. There is slight reduction in the flame spread rate with respect to the flow velocity. Thin case. Why? Because as I told you, in the thin case, the fuel burns and it consumes and goes away. Now what happens is as the flow velocity increases, then there may be some convective cooling which can occur, so that the flame temperature can reduce, so that the flame spread velocity will slightly decrease. On the other hand, if it is thicker, what happens is the heat up increases. The heat up, when the flame actually forms over this and spreads, the heat up of the solid will increase due to the convection. So you see the increasing flame spread velocity. But thin and thick, obviously thin reports a higher flame spread because it does not have any heating up. So the heat flux coming in is not wasted on heating up, it just burns. But in the case of thicker, the heating up, part of the heat is taken for heating up the solid. Okay, but in this case what happens is there is an increasing rate, but this rate is much below the thin cases. Now go to opposed. Opposed thin case, almost same value comes. Again, towards the end there is slight reduction. This is because of the convective cooling. In both thin and thick, we observe the same case for the opposed flame spread. It is steady, okay, irrespective of the velocity, it is steady flame spread rate. That is what we are trying to say. Okay, the slight reduction here is basically due to the convective cooling. So this is done by Pellow again. Based upon this only, the expressions were reported for the flame spread velocity. So what we observe here is concurrent flame spread is higher than the corresponding opposed flame spread. For thin, you can see that the concurrent flame spread rate is higher than the corresponding opposed flame spread rate for the thin. Similarly for thick. And in the case of concurrent thin and thick, you will see that thin has a higher flame spread velocity than thicker, because part of the heat is used to heat up the solid itself. Okay. So, experimental data is available for this flame spread rates. Now, the next topic is mass burning rate. Once the flame has spread over the solid, it is going to now consume the solid based upon the thickness basically. See, for example, we have a thicker solid, a flame has spread over the solid, okay. Then it is going to take away the solid material, consume the solid material slowly, and this rate at which it consumes will be steady mostly, okay. So, when you have a fire, so let us take in this case we have put a horizontal fire as established over the solid material. So, the burning rate can be calculated in a steady case basically using different expressions. So, we can think of say some 6 expressions. What is the, I put this fuel on a weighing machine and find the mass loss rate kg per second of the fuel itself, and this fuel has a calorific value or heat of combustion delta Hc. So, the heat release rate or the burning rate can be related to heat release rate. So, heat release rate can be burning rate into delta Hc. This is one expression. Now, gas phase, this is the solid phase basically. Gas phase, if we go, it will be same as this. The mass of the fuel coming to the gas phase, if that is known, that into delta Hc, because the same fuel vapors are going to come out. That is this heat release rate. Then, if I can measure what is the amount of oxygen which is consumed, then I know the heat of reaction per kg of oxygen, that product will also give you the heat release rate. Okay, so this is what, so oxygen comes, fuel comes, the diffusion flame forms and so on. Similarly, mass of CO2 into which is coming out, if I can measure that into the heat of combustion per kg of CO2 generated, that can also be the expression. Then I can say that density of fuel in gas phase into volumetric flow rate of the gases into CPG into average gas phase temperature minus initial temperature or the fuel initial temperature, that also will give you the the heat release rate. Similarly, take a control volume above the flame, and now what is the density of the gases? These are product gases now, into volumetric flow rate of the gases, average Cp of the gases into average temperature minus initial temperature or ambient temperature, we can say, that also will give you the heat release rate. So, basically the mass burning rate is connected to the heat release rate, and we can have so many expressions for this. So, I have listed here again these expressions for the heat release rate and the mass burning rates. So, solid mass loss rate into delta Hc, mass of the vapors coming into the gas phase or gases which is coming into the gas phase into delta Hc, mass of the oxygen consumed into delta H per kg of oxygen consumed, mass of CO2 produced into delta H per kg of CO2 generated. Then here average density of the fuel into volumetric rate of the fuel into CPG into average flame temperature minus the T0. T0 is the ambient temperature, initial or ambient temperature. Similarly, mass of the product gases which are coming out, CPG into average gas temperature. So, here you can see flame temperature is used, this is gas temperature minus T0. So, this is also is equal to, I can write mg dot as rho g, average density of the gases into volumetric flow rate of gases into Cpg into delta T. So, when you consider these expressions, normally radiation is not included. Okay. So, these are the mass heat release rate. We need, see, once a steady burning occurs, the heat release rate can be found. When heat release rate can be found, I can use this expression from the mass loss rate. So, any different types of calorimetries are available to measure the heat release rate. From that, I can find the mass loss rate. So, now theoretical approach for mass loss rate can be invoked, but unlike the liquid fuel, the mass loss rate expression for the solid fuels are quite complex because of the fact that, as I told you, there is no equilibrium temperature for the surface. When liquid burns, there is a equilibrium temperature, but here the temperature keeps on increasing. So, let us consider a vertical slab, any PMMA slab or wood slab, anything, and we ignite and a flame forms and covers the entire fuel, spreads over and covers. So, now this is the hydrodynamic boundary layer, this is the flame and this is the solid surface. So, now you can see some features here. First of all, due to the heating of the flame, fuel flux comes out and feeds the flame. At any x, this is the x direction. Now, understand that this is the x direction and this will be the y direction. And in the x direction, at any x, I will have a corresponding flame standoff, and this flame standoff is not uniform. Flame standoff increases and decreases. At a given x, flame standoff is called YF. Now, surface has a temperature Ts, due to which there will be some radiation which is given out from the surface to the ambient, re-radiation, that is. Now, some amount of heat flux can be conducted, solid conduction. So, conduction heat flux can occur, and here this heat which is provided by the flame to the solid can be due to radiation and can be due to convection, both. And so, from the flame heat is released, correct? Heat is released in the flame. Part of the heat is given to the solid by convection as well as radiation. Part of the heat is lost and part of the heat also goes out due to convection. This is lost to radiation. LR is lost to radiation, and part of the heat is actually convected away. The hot gases flows out and convected away. So, probably if the heat release rate is there, about 30% or 35% comes into the fuel surface, and a steady burning occurs consuming the fuel. Okay. So, this is the one where the gravity is in this direction and the entrainment occurs in this direction. So, this is basically the natural convection which is induced in this. So, the heat transfers are several. The heat released is lost by radiation and by convection. Part of that is given back to the solid surface using radiation and convection, and when the surface is heated up, based upon surface temperature, re-radiation occurs from the surface to the ambient, and from the surface in-depth conduction occurs basically. And here, when the flame is basically heating up, the pyrolysis length, and this is the flame height, xf is the flame height, and this is the pyrolysis length. Okay, now you can easily see that when the pyrolysis length is complete, the pyrolysis goes, all the pyrolysis gases need not participate in this distance itself. Within the pyrolysis length itself, all the pyrolysis gases need not participate. Some pyrolysis gases will go out and make the flame to extend over this pyrolysis length. The gases which are going out of this pyrolysis zone and feeding the flame after the pyrolysis length is called excess pyrolysate. This excess pyrolysate is consumed within the entire flame length. So, this is the total flame length. Pyrolysis occurs, that is, the fuel gases are generated only at a distance where pyrolysis has occurred. So, in the distance xp, pyrolysis gases are generated, it goes out and feeds the flame, but all the pyrolysis gases are not going to be consumed within this height itself, xp itself. So, some of the gases leave away and the flame is formed over this length of xp, and the excess pyrolysis feeds this flame, and the flame length is, the flame is said to be end where the excess pyrolysis is consumed. Okay. So, these are the features of the mass spectrometry. So, based upon this, some simplifications have to be done, then some theoretical analysis can be done. Okay. So, the pyrolysis evolved at a specific velocity called blowing velocity. So, when there is a condensed surface and mass transfer occurs, okay, there will be induced velocity. So, I will say fuel velocity. This velocity, fuel velocity, is called blowing velocity or Stephen velocity. In the case of the liquid fuel, we have seen that the Stephen velocity is induced. The problem itself is called Stephen problem. So, this is the Stephen's mass transfer velocity. When there is a condensed phase, that is the fuel gases are coming out of the condensed phase, we get this velocity. So, now this, by convection as well as diffusion, this flux which is coming out of the solid surface feeds the flame. Okay. Now, what is burning rate per unit area? Some mass of the fuel comes out at a particular rate, that by unit area will give you the flux of the mass which is coming out, that is rho A V is the mass burning rate. When you divide by A, you get rho into V, where rho G is the density of the gases which are coming out, and Vg is the velocity of these gases, and the unit is kg per meter square second. Now, for steady burning, the heat balance at the solid surface will be the heat flux, that is the heat flow rate per unit area will be equal to m dot double dash into L, where L is the heat in joules which is required for releasing the pyrolysis. So, I can say L is the heat of pyrolysis, So, that will be the balance of heat. So, the mass is coming out is rho G into Vg, that is flux per unit area. Similarly, the heat flux will be m dot double dash, that is rho G into Vg into L, where in turn this is heat of pyrolysis plus sensible heat. L is called heat of pyrolysis plus sensible heat, that is the heat required to release the pyrolysis. So, L can be expressed as a sum of delta Hp, which is called heat of pyrolysis, and Cp solid into Tp minus T naught. Tp is the temperature of pyrolysis or ignition temperature minus the initial temperature of the solid. So, we can write these expressions. Okay. So, now the net heat flux to the surface depends on the nature of the flow field and boundary conditions. Correct. So, if it is convection, etc., or the freezing temperature, how it is, what is the concentration, etc. So, this heat flux will depend on that. Okay. Now, there is an effect called blocking effect. When you do not remove the vapors as soon as, or gases, as soon as they come out of the solid surface, then that will lead to blocking effect. This is like in the case of liquid fuel, we saw that the accumulation of vapors over the solid surface will decrease the evaporation rate. Similar to that, when you do not remove the gases coming out of the solid surface, it will create a blocking effect. If the net heat flux to the surface increases, then the mass flux or the mass loss rate per unit area will also increase. Then the boundary layer will thicken. Then the gradient will reduce. So, the diffusion transport will reduce basically. A large burning rate, when you have a large burning rate, from the surface a flame is formed. Okay. like this, a flame is formed over the surface. So now when the burning rate is large, then the flame standoff will increase. That is, the flame is said to be pushed farther away. So the flame standoff will increase. Flame will be closer to the surface if the environment contains more oxygen, because why these gases have to travel more distance, because it has to get the enough oxygen. But if the oxygen concentration increases, the oxygen uh, availability will be increased, so that the flame standoff decreases. Then the burning rate therefore does not increase linearly with heat flux. Okay, so that is another important point. When heat flux increases, we need not always say, because the blocking effect comes into play, thickening of the boundary layer, etc. occurs. Flame is pushed out. When mass burning rate increases, flame is pushed out. So this means that there are counter effects. Only heat transfer will not be able to do this. While predominantly heat transfer can increase the surface temperature, but it cannot always assure that the mass burning rate will increase. So it can be assumed that the heat flux to the surface is a product of a global heat transfer coefficient H into delta T, that is Tf minus Ts. Okay, but this H should include radiation and convection. So H will be the overall heat transfer coefficient, which is H convection plus H radiation. So I will say H equal to HT, total heat transfer coefficient. So now I can say m dot will be equal to q dot double dash by L. L is the latent heat plus the sensible heat. So H into Tf minus Ts by L, or B into H by Cpg. B into H by Cpg, where B again is the transfer number. We have already seen for the liquid case, BQ we saw as Cp G T infinity minus T S divided by H of G. Similar to that, I get Cpg equal to Tf minus Ts divided by L. Okay. So now if you substitute that, I get the mass. So basically you need to make some approximations and do this. So now in order to calculate H, I need Nusselt number. Nusselt number is a function of Reynolds number and Prandtl number for forced convection, and is a function of Grashof number and Prandtl number for free convection. Okay. So this is the theoretical basis for the mass burning rate, where we can see that there are complexities in terms of heat and mass transfers, and when you try to simplify them, we get some expressions where we see the similarity between what we got for the liquid and the solid fuels, the mass burning rate, steady mass burning rate. However, again that H determination is not so straightforward. In the case of liquid fuel, there is no H which was actually used. Okay. So now the Nusselt number expression can be used here. So Nu equal to H, the previous what I wrote, H x by K, x any Nusselt number any x kg. So now Kh can be written as Nusselt number into kg by x, Nusselt number into kg by x. So B by Cpg into H can be written like this. Okay, now convective conditions, as I told you, and there are two things: forced convection, natural convection. Whether it is laminar or turbulent, we need to use appropriate correlations for Nusselt number. We have to use that and get, maybe these correlations are empirical based upon several experiments. The Nusselt number correlations for the fire scenario will be got, and based upon that we get, as I told you, normally Nusselt number is correlated to Reynolds number and Prandtl number for forced convection, and the Grashof number and Prandtl number for the natural convection. However, the expressions will be empirical in nature depending upon the laminar or turbulent regime. Okay. So, I stop here. This completes the fourth module. I will continue with some case studies in the next class.